ones I gave you last week. It's in your sheet.
On my blue?
Yes, and your blue one.
No, hold on. How are you supposed to do that? I'm thinking it's like.
Oh, this is. Where? Linda? Yeah, it's wrong date. If you have questions, ladies and gentlemen, call me over. I will be happy to help you. Yeah. Well, whatever his name for the uniform next year, you got it written on there. You actually have it written, a definition for it. Is that an evenly distributed or uniform? There you go. You bet.
Mr. Graham?
Yep. Yeah, is represented by three. So, and I am gonna go over that as well today, so. I will go over your quizzes after we do this, ladies and gentlemen, okay? So, let me find your shining. Shining normally fourth hour, right?
Yeah.
Shining, what class do you normally have first hour? Are you off campus?
Okay.
Okay. Just so I don't know not to send down anything for attendance.
Yeah.
I'm ready to go. You're fine.
Couple minutes left, ladies and gentlemen, then we'll go over this. Okay. One of the things that I'm showing you in the clues today, ladies and gentlemen, is sometimes the answer to one clue is dependent on where you place another. In the first three questions, ladies and gentlemen, they are all reliant on where you place the answer in the first question. Okay? You mess that up, you're going to have problems with the next two. But also, the next two can help you place that first one if you didn't get it in the right spot. The other thing, on the test, ladies and gentlemen, you can buy an answer. You can ask me to place any element that you want on the periodic table, and I will place it in the correct spot for you. But it costs you the 2 points you would have earned for that element. However, if there are two other clues that depend on where one is placed, and you know where those two go depending on that one, you could have me place that one, and I will place it on the test for you. So just an option. Okay? The element name for a uniform mixture is often considered a family by itself since it can act as a metal and a non-metal. All right, the element that is named for a uniform mixture, Madison, what do you got? Okay, what's the symbol? HO, homogeneous. By the way, again, it is great that you are writing these things down on your blue periodic table or on your blue sheet here, ladies and gentlemen. But if you forget what you got written there and you got to look it up anyway, you're in trouble. This has got to be the easy part. Finding your answer on here shouldn't take you long so that you can get to the next part. Now, what element is a group unto itself, is a family unto itself, and can act as a metal and a non-metal, Alicio? It is hydrogen. So what group is hydrogen in, Alicio? And what period? Yep. So group 1, period 1. Any questions on that, ladies and gentlemen? Remember, on the test, it's going to be blank. You will go to the spot where hydrogen normally is now, and you will write HO there. That is the clue that will go there. We will practice this later this week and early next week. But right now, all we're doing is saying, okay, what element are we placing? And where are we placing it? Group 1, period 1 is the spot where hydrogen normally goes. So in that spot, we are going to put HO for homogeneous. Okay? All right. The element branium combines to make a life-needed compound of HO2B. What life-needing compound is similar to that, especially when you consider where HO is on your periodic table? It's taking the place of what? Well, HO is taking the place of hydrogen. So what life-needing compound are we talking about? We're talking about water, H2O. So where would branium go? Symbol B, we got that. Where would it go? Thank you. Group 16, period 2. Okay, so that is where you would place it. You would place it in the spot where oxygen normally goes. Okay? This element named for energy being released from a reaction would be isoelectric to B minus 2 as an ion. All right. What element is named for energy being released? Elsa, what element is named for energy being released on your blue sheet? EX, exothermic. Thank you. All right. Now, here is where B2, B minus 2, would be on your periodic table, in the spot marked for oxygen. It is a nonmetal. Nonmetals are always isoelectric to what? What element are things isoelectric to?
Noble gases.
Good, the noble gases. So now the question is, which noble gas is oxygen, this one, because that's the spot where branium goes. Which noble gas is this isoelectric to? Neon. So since B negative 2 would be here, EX, exothermic, would go where neon goes. It would be in group 18, period 2. Questions? All right. The element named, that should say for the shortest wavelength form of visible light has electrons arranged in the following way. The K has 2, the L has 8, the M has 18, the N has 32, the O has 18, and the P has 3. So, element name for the shortest wavelength form of visible light. What is the shortest wavelength form of visible light, Jesus? At the top of your sheet, it is labeled what wavelength does as you go across that spectrum. Which one has the shortest wavelength form of visible light? VI for violet. Very good. Okay. K2L8, M18, N32, O18, P3. Now, give me one of two ways you could find this, ladies and gentlemen. What could you do? Add them all up. 2 and 8 is 10, 28, 60, 78, 81. What element is 81 on the periodic table? Thallium. Thallium is in group 13, period 6. Group 13, period 6. Anyone have another way of doing it? One, two, three, four, five, six. Sixth energy level, 3 valence electrons. Sixth energy level, 1, 2, 3 valence electrons. Please remember, the S's and the D's are one behind. They are not in that final level. So that would get you to thallium as well. Questions? Okay. This unreactive monatomic gas, what is that telling us, Dania? Unreactive monatomic gas. It's what? What's that telling us? Group, period, which? It's in group 18. Very good. That is in group 18. Is in the same period as the orientations of an F orbital. Now, how many orientations? Not the number that represents an F. How many F orientations are there? 7. Okay? And is named for the unit for amount of substance. What is the unit for amount of substance? Mole. What is it for mole? M. Questions? So, violet has the shortest wavelength. Okay, again, we asked you to put this onto your periodic table. This is what we asked you to put across the top of your periodic table. I asked you to label microwave, infrared, red, orange, yellow, green, blue, violet, ultraviolet, and gamma. Those are the only ones that are on your blue sheet. I left off radio and TV. I left off X-rays. By the way, you ain't got time to copy this now. It's on the back table in the back. You can copy it or take a picture of it before you leave. I'm not leaving it up there because I've already done this. Wavelength as you go across this decreases, meaning microwaves to gamma, gamma have a shorter wavelength, meaning red to violet, shorter wavelength, further to the right. Frequency and energy both increase as you go across. So microwaves, low frequency, low energy. Gamma, high frequency, high energy. Red, low frequency, low energy. Violet, high frequency, high energy. That is the pattern that goes across. Questions? Now, I will tell you, on the test, sometimes it just says orangium is a third period noble gas. Okay? You're not going to have to figure out which one it is. It'll tell you that. But I do use clues like they're arranged in order of decreasing wavelength. So you got to put them in order of decreasing wavelength, things like that. Questions? All right, let's take a look at your quiz real quick, ladies and gentlemen. Okay? Now, the answers that are highlighted in pink are the answers from version B. The answers that are highlighted in yellow are from version A. The answers are in the same order for either version, all the way down. Your quiz is right on my desk there, Wendy. Okay? Yep, that's yours. Okay? So, clue number 1, version A. I'll go through them real quick with you. The element name for the symbol of wavelength, that is lambda, is a monatomic element in the same period as the number that represents an F orbital. The number that represents an F orbital, S is 0, P is 1, D is 2, F is 3. Third period. Third period. For version B, the element name for the symbol of wavelength is in the period that can act as both a metal and a non-metal. So that would be period 1, group 1, because that is the spot of hydrogen where something can act as a metal and a non-metal. Clue number 2, the element name for half the height of a wave, amplitude, AM, is stable as a +2 ion and has the largest mass in its family. So, group 2 is the +2 ion, largest mass is in the 7th period. Version B, the element named after the high point of a wave is a monatomic element in the same period as the number that represents an F orbital. So that is 18 and 3 as in question 1 for A. Question 3, the element name for the form of visible light with the longest wavelength. Longest wavelength in visible light is red, Re. Okay? Is an element on the periodic table that can act as a metal or a non-metal. So that is group 1, period 1. That is the spot of hydrogen. The element named after the school color of East High School is a man-made halogen. Halogens are in group 17. Man-made one would be in period 7. Clue number 4, the element that is a +3 ion is in the same period as the number of electrons that fill the p orientations. 6 electrons fill the p orientations in an atom that is named for a bundle of electromagnetic energy. So a quantum is a bundle of electromagnetic energy. -3 family is group 15, and there are 6 electrons that fill the p orbital, so that would be period 6. For the other version, the element name for a bundle of electromagnetic energy is the heaviest nonmetal to have 6 valence electrons. 6 valence electrons is group 16. The heaviest nonmetal in group 16 is period 5 because the 2 and 6 and 7 are metals. Questions? All right, clue number 5, ladies and gentlemen, version A. The element name for the unit of frequency, hertz, is a metal in the alkali metal family and is in the period as the same number of d orbitals. So the alkali metals are group 1. There are 5 d orbitals. 5 d orbitals. The element name for the unit of frequency is stable as a +2 and has the largest mass in its family. So therefore that is group 2, period 7. Again, same question as the other one, just a different order. All right, number 6, ladies and gentlemen. The element name for the longest wavelength type of EMR. That is all of them. That is not just the visible light. The longest is microwave. Okay? The longest is microwave. Is the heaviest nonmetal with 6 valence electrons. Group 16, again, period 5, because 6 and 7 are filled by metals. In version B, the element that has a -3 ion is in the same period as the number of electrons that fill the p orientations. -3 ion is group 15. There are 6 electrons that fill the p orientation, so period 6. Finally, number 7, the element named after the school color of East High is a man-made halogen. Group 17, period 1 for red again. I repeated this one, sorry. The element named for the form of visible light with the longest wavelength is a metal in the alkali metal family, group 1, has the same number of d orbitals, period 5, and that would be red. Questions, ladies and gentlemen? This is very similar to what you are going to see on your test. Questions? Okay, now, you do not have to, but if you want to take out your computers, you can. I'm going to go through the history of the atom today. A more important thing would be to have out your blue sheet. And as I go through a scientist on here, write down next to them what the major thing they did is, and I will tell you what the major thing they did is. But before we do that, ladies and gentlemen, I do have a couple of slides that I need to talk to you about real quick. Okay? A long time ago, we told you that certain transition metals can have more than one charges. Copper can act as a +1, copper can act as a +2. Now that we understand a little bit about quantum numbers, now that we understand about how the electrons fill, we can kind of explain this to you. Okay? Again, not going to test you on this. The test is about placing those elements. But there is this thing called the degenerate orbital. What a degenerate orbital is, an electron sometimes will get promoted from one energy level to another, even if it's a little bit higher energy. And it happens because they're trying to not pair up in an area, or they're not filled singly first and then doubly. So what happens is, here's how we explain copper being a +1 ion. There are supposed to be 2 electrons here in the 4s. They are supposed to fill before the 3d. The only way to explain how copper can be a +1 is if one of these electrons goes and finishes filling this 3d. So now there are 3ds and they are all filled. We have the same number of electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, 21, 23, 25, 27, 31 electrons here, ladies and gentlemen. Okay? So this would be copper as a +1. It would take the 1 electron from here, move it to here, and then it'll eventually lose this 1. That's how it can be a +1. If it doesn't kick an electron up into there, it just loses both of them, and that's how it can be a +2. Now, why some copper does this and some others doesn't do this, we don't know. We don't know why this happens, but this is the only explanation for it. Again, not getting into this very heavily, but these are in the outer energy level. These are in the outer energy level. If you lose this 1, you become a +1. If you lose these 2, you become a +2. That's the explanation for it. That is why iron can be a +2 and a +3 in certain atoms. That is why copper can be a +1 and +2. That is why we ignored the middle transition elements on the periodic table and continue to do so most of the time today. The second thing, ladies and gentlemen, and this is what we finished with last week, was there is what is called being isoelectric. Okay? Isoelectric is the same electron configuration as a noble gas. Metals can do this, non-metals can do this. Now remember, all atoms want to become stable. They want to gain or lose electrons to become stable, but they can only do it in a compound. But when they do it, ladies and gentlemen, when fluorine gains 1 electron to become a -1, it now has 10 electrons and it is isoelectric to neon. When oxygen gains 2 electrons to fill its outer shell and become stable, it looks just like neon as well. So does nitrogen, so would carbon if it were to gain 4 electrons. Nonmetals are always isoelectric to the noble gas at the end of their row or period because they are gaining electrons. Metals are losing electrons. Aluminum will lose 3. That means it'll only have 10. That means it looks just like neon. Sodium or magnesium will lose 2, meaning it will only have 10 as well when it is stable, looking just like neon. Sodium loses 1, looks just like neon when they become stable. So, things are always isoelectric to noble gases, ladies and gentlemen. And for metals, it is the noble gas that is one row above and at the end. For nonmetals, it is the noble gas at the end of their row. And this is only if they actually have a charge. So like today's clue about branium being a -2, that has a charge. That is then isoelectric to a noble gas. You do not become isoelectric and look like anything other than a noble gas. Because if you are, you have not yet become stable, and you're not going to go part way to becoming stable. You're not going to gain 1 electron and become a -1 if 2 makes you stable. You're going to gain both of them. Questions? Okay, so here we go, ladies and gentlemen, atomic history. Now, I would like to preface this, ladies and gentlemen, by saying a couple of things. Number one, this history goes back a long time. Matter of fact, it begins 400 BC. BC. So that is about 2,500 years ago. Okay? Number two, for a long time, scientists were not very well respected because science and religion conflict. And scientists who were practicing science, the church viewed them as practicing witchcraft. So scientists didn't go to parties going, hey, I'm a scientist, I'm working on doing this. No. A lot of times they didn't say anything. Okay? So for a lot of the history of time, scientists didn't share information. They didn't publish what they knew. Okay? Because it could be traced back to them. Number three, when you found a scientific discovery, you had to bring it to a board of scientists who would approve your work. They would look at it and say you did good work or you didn't do good work, and therefore your conclusions are not valid. They were all male, ladies and gentlemen. So any females who did work very rarely got credit for it. Okay? So that's a little bit about the atomic history, ladies and gentlemen, and here we go. Again, it started with a Greek philosopher named Democritus. He is on your periodic table. He started out the theory of the atom. Okay? It was called the discontinuous theory of matter. And the story goes that he sat down to have dinner one night. And he had a loaf of bread in front of him, and he cut it in half. And it got him to thinking, can you cut things in half forever? Can you always divide it up into some smaller part? Or do you eventually hit something that cannot be divided? And he believed there was some part that could not be divided. That's why it is called the discontinuous theory of matter. It doesn't continue to be broken down and broken down and broken down forever. There is some small particle out there that cannot be divided and cannot be destroyed. He called that atomos. He called that atomos. We call it atoms today. But that was at about 2400 BC, or about 400 BC. I am not quizzing you on dates. Just doing it to give you a little idea of the history, ladies and gentlemen. Okay? Then along came a man named Proust. Now, Proust created a law. Laws are important, ladies and gentlemen. Proust is on your list. He did the law of definite proportions. And basically what he said, ladies and gentlemen, was that things combine in a certain ratio. And it is a proportion. There is so much of this element to so much of this element. And he believed that hydrogen is the building block for all elements. That a helium atom was simply 2 hydrogen atoms that slammed together and made a larger one. A lithium was 3 hydrogen atoms that slammed together and made a larger one. And you know what? Even though he had no clue, he was absolutely right, because we see this happen in the giant nuclear reactor we call the sun. The sun is so massive that it can literally take 2 small hydrogen atoms, slam them together, and make a helium atom out of them. In the U.S., or in our world, we do not have the technology to slam 2 small atoms together. we slam two big atoms together and make a bigger one. Those are the last ones that are man-made on the periodic table. Why? We can't make two small atoms hit hard enough to fuse together, but we can make two larger ones do that. Okay? So Proust created what was called the law of definite proportion. In water, he realized that there was a certain amount of hydrogen to a certain amount of oxygen, a proportion by mass of 1 to 8. Now, you're sitting there going 1 to 8 in water. Well, there are 2 hydrogens and there is 1 oxygen. 2 hydrogens would have a mass of about 2. 1 oxygen has a mass of about 16. 2 to 16 reduces down to 1 to 8. That is a definite proportion. Okay? All right. Along came a man named Lavoisier. He was a French scientist. He gave us the law of conservation of mass. He is on your list. Put down law of conservation of mass. Okay? Now, he did experiments with a new piece of equipment, ladies and gentlemen. We started to develop a very precise balance. Okay? Now, I love to tell this story because it's just interesting. Not anything I'm going to quiz you on. But Lavoisier was a Frenchman. And the French, what kind of a government system did they have back in the day? Monarchy. And in a monarchy, there's one very simple rule. Don't piss off the king. Because if you pissed off the king, what would he do? Execute you. How did the French choose to execute people? They chop off their head. Well, Lavoisier got a little, full of himself when he's making all these scientific discoveries, and he spoke out against the king. So the king sentenced him to death by guillotine. They would walk you out into the public square, they would stick you in there, boom, chop your head off right in front of everybody. Why? Hey, I can do this to them, I could do this to you. This is the way it works. Lavoisier did one last experiment, ladies and gentlemen. He told his assistant that if they cut my head off and I live for a short period of time, I will signal you. I will blink. Cut his head off, pulled the head out of the basket, and he blinked 19 times before he finally closed his eyes. Shortly after that, they stopped executing people by the guillotine because they said it wasn't humane. They always thought it was. Head gets chopped off, you're dead right away. Doesn't work that way. Next came a man named Dalton. Dalton is the father of modern chemistry. Dalton is the person who really, after Democritus gave us the idea of the atom, it is Dalton who started the atomic theory. What we are talking about now. How the atom is made up, makes up everything, and what the atom is made up of. He created an atomic theory. He said atoms are indivisible and indestructible. All atoms that are alike are exactly alike. Atoms that are different. Yeah, no brainer. Thanks, dude. And atoms can combine to make compounds. Atoms can combine to make compounds. Matter of fact, he solved a problem that Proust was having. Proust gave us this law of definite proportions. But his proportions didn't work out every time. I would know this one, and I would know any law. That one for sure. Okay? Proust had a little problem with his proportions in that they always didn't quite work out. Sometimes they weren't the same. Well, the problem was he was finding that 2 different elements could combine in multiple ways. Couldn't explain it. Dalton did. So, for example, you and I exhale carbon dioxide. 1 carbon, 2 oxygen. When you burn things, you create carbon monoxide. 1 carbon, 1 oxygen. Same 2 ingredients, 2 different proportions. Dalton said you can have multiple proportions of the same 2 elements in a compound. Proust didn't realize that. All right, now we get to a scientist named Berzelius. He is on your list too, I believe. Yep, 3rd one down, ladies and gentlemen. He found the relative atomic masses of most of the metals on the periodic table. Okay? He found the masses of most of the metals of the periodic table. And he did so by comparing metal oxides. So maybe after you write down that he found the mass of most metals, put metal oxides on there. Okay? So, again, a lot of elements that were on the periodic table, very rarely do you find them alone. So he studied them in compounds that contained oxygen because metals like to combine with oxygen, and he was able to find the mass of many of the metals on the periodic table.
Would you say
I would put metal oxides afterwards, just so you know. That's what he studied, was the metal oxides, to find the masses of the metals. Other questions? Davy's on your blue sheet. Okay. Davy gets credited with discovering most of the alkali metals, ladies and gentlemen. Now, the alkali metals are the most reactive metals on the periodic table. You very rarely, if ever, find them alone. But Davy is the man who discovered most of them. Okay? He is the man who discovered the alkali metals. Okay? He found more new elements than anybody else. So maybe after the alkali metals, you put found elements. Found more than any other person he's credited with. Questions? So again, I can see me asking a question. The scientist who discovered the alkali metals is a third period noble gas. The scientist who gave us the law of conservation of mass is a second period alkali metal. Okay? I'm not asking you to memorize these, but again, write it down and make sure you look it over occasionally. Why? You want to be able to find your answers quickly. Okay? You want to be able to find your answers quickly. Okay, go back to the next slide. All of this is in your EISN as well, ladies and gentlemen. It is all in these slides. There's nothing for you to fill out on there. All of this is on there. So what you're seeing on the board is in your slides. Please remember, on the test, I don't care if you use your slides or my master slides. My master slides, what I'm showing you, are out there for you to use on the test. All right. So now we get to a man named Dobereiner, ladies and gentlemen. Dobereiner started to organize elements into what were called triads. He put elements together that had similar properties. Now this wasn't, remember, the periodic table was not set up yet at this time. So what he did is he looked at elements and said, you know what, these three are all kind of alike. These three are all kind of alike, and he called them triads. Now I want you to just look at a minute here, ladies and gentlemen. These are a couple of his triads. He put magnesium, calcium, and strontium together. He did a pretty good job. They're in the exact same family. They have the same charge. They react the same way. He also put iron, cobalt, and nickel in a triad, right next to each other on the periodic table. He also did copper, silver, and gold. Copper, silver, gold. He did a pretty good job, ladies and gentlemen, putting these elements together because they had similar properties. Okay? His was the first kind of attempt at doing a periodic table, but I will tell you this. What I ask you about on the test is the guy who created triads. Okay? The guy who created triads. And if you want, it isn't going to hurt anything, but... Alright. Now along came a man named Newlands. Newlands was an interesting scientist because he was a musician turned into a scientist. He was a classically trained musician who studied science as well. Okay? Now, that is kind of a bonus part to the clue, not really what I would ask you, but he gave us something called the law of octaves. Any music people in here? What's an octave?
8 notes apart.
8 notes apart. Kind of like the 8 groups on the periodic table that are on the periodic table I gave you. Again, not including transition metals, not including the ones at the bottom, but what Newlands found was that there was a pattern that after 8 elements repeated again. Then you got the same kind of pattern. Then it repeated. So again, he is credited with what is called the law of octaves. Okay, next came Meyer, ladies and gentlemen. Meyer was a German scientist who tried to set up an actual periodic table. he and another scientist were competing to form the periodic table that we see on the wall, ladies and gentlemen. Okay? So, he was working on one, and another Russian scientist named Dmitry Mendeleev was working on one. Now, the difference between them was Mendeleev predicted that there were elements that had yet to be discovered on the periodic table. Meyer just tried to set up all of the known elements into a periodic table, into groups, into families. Eventually, ladies and gentlemen, we have adopted Mendeleev's periodic table. That is the scientist who gets credit with doing our current periodic table, is Mendeleev. Meyer was competing with him. And the reason Mendeleev's got accepted is because he left blanks or holes in his periodic table. Now, at the time, the science community who had to look at everybody's work was like, dude, you left holes in your periodic table. He's like, yeah, I know, those are elements that are not discovered. They're like, yeah, sure, elements not discovered. Good, so you can't explain something, so you just left a blank and you expect us to buy that. He's like, no, I'll tell you what. When they find this element right here, here's going to be its mass, here's going to be its properties, here's going to be its density. And when they started finding him and he was right on all of those things, they're like, okay, we'll give you credit for the periodic table. Because he predicted elements that had yet to be found. Okay? Question. All right. Next came a man named Melville. By the way, this is not the same guy who wrote the book Moby Dick. Different Melville. Okay? He worked with a Crookes tube and found that different gases created different colors. Different gases would glow different colors when you put electricity through them, ladies and gentlemen. Okay? So, Melville found that gases created different colors, which means they had to be different gases. Now, you remember about Davy? Davy did what? Discovered alkali metals. And he found these because they were combined with a lot of things. He just had to isolate them. But alkali metals were in a lot of compounds. Guess what's real hard to discover, ladies and gentlemen? Gases. They're colorless. They're odorless. Yet they're around us, and they're hard to detect. When you grab a chunk of ore, you can see the thing and you can separate the different parts of it. Hard to find gases. Melville was the guy who started to find different gases. Why? Because they would glow different colors in a Crookes tube, meaning they had to have different properties, meaning they had to be different gases. Okay? All right. Now, by the way, we still know nothing about protons, neutrons, and electrons. Nothing. Okay? But along came a scientist named Millikan, and he did what we call the oil drop experiment. He took oil and sprayed it as a fine mist between two charged plates, two electrically charged plates. And he could get the particles to suspend there in between these two charged plates. And then if he would adjust the electricity on one a little bit more than the other, he could get the particles to move one way or the other. That was the oil drop experiment. Yep, that's what I would write down. But he also started to quantify the charge on the electron that we didn't even know was an electron yet. He realized that matter was made up of charged particles. And he could tell what the charge was on an electron before we even knew what an electron was by doing his experiment with these plates. Oil drop experiment, quantified charge. Questions? Now came a man called Thomson. By the way, we're about in the 1920s, 1930s, 100 years ago now. Still had no idea about protons, neutrons, and electrons until Thomson. Thomson gave us what is called the plum pudding model. Why? Because he found the electron, ladies and gentlemen. He was the first scientist to find the electron. He said there was a negatively charged particle within matter. And he gave us what he called the plum pudding model. Now, I have never had plum pudding. Anybody in here ever had it? Good, because I think plum pudding went away in like the 1930s. But when I was a kid, my mom would make chocolate pudding. And then what she would do right before she served it to us is she would grab the jar of maraschino cherries and she'd put cherries in with the chocolate pudding. Now, cherries are good, chocolate pudding is good. You put the two together, it's greatness, ladies and gentlemen. Okay? Well, what would happen is you'd be eating your chocolate pudding, and every once in a while you'd get a cherry. Just randomly spread out throughout it. That was the idea behind the atom. Somewhere within the atom there were these negatively charged particles, these electrons. Didn't know where, but they were randomly spread out, like plums and plum pudding. There are some who call him the chocolate chip cookie model because it's more something that you can relate to, like the chocolate chips would be electrons spread out throughout the cookie. Kind of his idea. Okay? But what this really means, ladies and gentlemen, is that the atom is now divisible. The atom is not one small chunk of matter. It is made up of smaller pieces. Okay? Now, he found the electrons, which were negatively charged, which meant people also believed there must be a what charge? A positive. Didn't find that, but people realized that there's a negative part, there's probably a positive part as well. Okay? All right. So here comes a man named Rutherford. Again, we're about the 1930s, somewhere in there, ladies and gentlemen. Rutherford said the atom was mostly empty space. He did what was called a gold foil experiment. And he fired positively charged alpha particles at a thin sheet of gold foil. And he found that a lot of these alpha particles went right straight through and didn't touch a thing. Right straight through, did not touch a thing. So he said, well, the atom has to be mostly empty space. But what he also found is that if these positively charged particles hit something, they bounced off it and away from it. That was not what he was expecting, because what was supposed to be scattered out throughout the atom? The negative charges. And a positive and a negative should what? Attract. They didn't. Whatever he hit, they bounced off of. He proposed that that was the nucleus of the atom, ladies and gentlemen. He said that was the nucleus, okay? And he gave us a solar system model to explain it. He said the nucleus was like the sun and electrons are like the planets orbiting it. Now, while this may sound like a weird idea, here's a periodic table, ladies and gentlemen, from 1930. Revised edition, 1930. Up in the corner there it says planets valence, meaning the electrons in the outer rings of an atom. Planetary electrons in completed orbits. This was taught in classrooms, ladies and gentlemen. They believed that electrons orbited the nucleus like planets orbited the sun. Okay? And as little as 100 years ago, when Mr. Arts first started teaching at East High, that is what they taught. Okay? All right. That wasn't until a man named Niels Bohr came along. And he proposed what is called the quantized electron. He said that electrons have a certain amount of energy depending on where they are at around the nucleus of an atom. Guess what? He was right. He said the electrons are in energy levels. They are not in orbitals. Orbits mean you could predict where they will be. Energy levels are an area around the nucleus where electrons are likely to be found. And we fill the lowest energy level first, and then the next lowest, and then the next lowest, and then the next lowest. And what do you know? You get 7 periods that represent 7 energy levels for electrons, ladies and gentlemen. Okay? So Bohr gave us that idea. Again, we still have yet to find the proton. Planck, remember him? Gave us Planck's constant. When we started this unit, we talked about wavelengths, frequency, energy. He gave us a constant that related energy and frequency. Well, he's the one who gave you those wonderful quantum mechanics and quantum numbers that we were working on at the start of the year, ladies and gentlemen. He discovered, created, came up with quantum mechanics. Okay? He gave us the quantum numbers, ladies and gentlemen. And yes, he has a constant named after him. Okay? So, he discovered quantum mechanics, gave us quantum numbers, this model where we could identify every electron around the nucleus of an atom. And he gave us a constant that relates energy and frequency. By the way, we're probably around the 1950s right now, somewhere in there. Questions? Moseley, guess what? He found the proton. Moseley gets credited with finding the proton, ladies and gentlemen. And now our periodic table that Mendeleev set up, we can add atomic number to it. Okay? We can add atomic number to Mendeleev's periodic table, which, by the way, did not change. He had things in the right order, understood them very well, even as we're now adding the atomic number to the elements on the periodic table, ladies and gentlemen. Questions? I think we got one more slide to go. We're getting there, promise. Heisenberg, ladies and gentlemen. Is he on your list? Ooh, man. He gave us what is called the uncertainty principle. Now, what that means, ladies and gentlemen, is the uncertainty principle says that it is mathematically impossible. You can't do it. You cannot find the speed and the location of an electron at the same time. You get one or the other. You get its location or you get its speed, but you cannot have both. Still true today. We can know how fast an electron is moving, or we can know an area where it is moving, but we cannot know both. Okay? And that was those orbital shapes that I showed you, the barbell, the sphere, those. We know about where they're located, or we know how fast they're moving, but we can't tell both. That's the uncertainty principle. Question? This is the first thing you're writing down? You good? No? Come on. Pauli gave us the exclusion principle, ladies and gentlemen. You already know what the exclusion principle is. No two electrons can have the same set of what? Wow, I was hoping we would get this. No two electrons can have the same set of 4 quantum numbers. Every electron's quantum numbers are unique or different. No two electrons can have the exact same 4 quantum numbers. Can't be done. Nope. That is the exclusion principle. Every electron gets its own unique set of quantum numbers. Avogadro, we already have talked about him. He gave us the mole concept, formula mass of the elements on the periodic table are all related to one element, and that is carbon, ladies and gentlemen. Atoms are so small, we have no way of actually putting them on a balance and measuring their mass. So the numbers on the periodic table that you see for average atomic masses, those are relative to the element carbon. That's what they're based on. Carbon has a mass of 12.011, hydrogen 1.007. That means that hydrogen's mass is about 1/12 of carbon. So that's what that means. Avogadro gave us this mole concept. Newton, ladies and gentlemen. Yep, that's the guy, Isaac Newton. Right? Famous scientist. He said that white light was made up of all of the colors of the rainbow. He gave us Roy G. Biv. Said white light was made up of all of the colors of the rainbow. And what happens, ladies and gentlemen, when electrons move around from one energy level to another, takes energy to move up to a higher level. You take away that energy, they move back down and release that energy. When they release that energy, it's one of the forms of light. Red, orange, yellow, green, blue, indigo, violet. Okay? White light is made up of all of the colors of the rainbow. That's it. That's the last guy. Awesome. Questions? Okay. So, in reality, ladies and gentlemen, you should have nothing by, Einstein. Anybody got anything by Einstein? E equals mc squared. Einstein gave us the equation E equals mc squared, probably the most famous equation in all of science. E equals mc squared. Now you should not have anything by intra and intermolecular. We have to get to that yet. You should not have anything by London dispersion forces. And you should have nothing by van der Waals. Other than that, we have covered everything on this sheet. Okay? So those are the ones that I have to get to yet. And if you are a senior, those will obviously not be on the questions that you are taking on your test. Okay? They will be on everybody else's because I will get to them. Okay? All right. Take out your periodic table, the one that looks like this, please. We're going to, and if you want, I have highlighters up here. I'm going to highlight certain areas. You could come up and grab one if you want. You do not have to. It is your choice. But they may be wise for you to do so. Okay. In period 4, groups 2 through 13, and in period 5, groups 2 through 13. These 4 boxes right here, ladies and gentlemen, we are highlighting those. And why are we highlighting those, ladies and gentlemen? Well, let me tell you why. What color haven't I used yet? I haven't used green. What? Pull it down a little bit. Thanks. I wasn't sure why you were asking me to do that. All right, we're going to use orange. All right. So in this area, ladies and gentlemen, even though these are next to each other, these elements, atomic numbers, differ by 11. Even though these two elements are right next to each other, their atomic numbers differ by 11, and let me explain why. Calcium is right here. Its atomic number is 20. The next element is gallium. Its atomic number is 31. Okay? So even though they are right next to each other, they differ in atomic number by 11. The same with strontium, 38, and indium, 49. Okay? So here's what I'm telling you. I will give you a clue, something like the elements named after the ways energy can go in a reaction. There are two of them. What are they? The elements named after the way energy can go in a chemical reaction. But what are the elements? Exo and endothermic. Are right next to each other on the periodic table, even though they differ in atomic number by 11. Meaning they have to be here or here. And they're in the first period where d electrons fill. Which period do d electrons start filling in? So that would be right here. The one named after energy going in is lighter than the one named after energy going out. So which of these two elements is lighter? The one on the left or the one on the right? Left. Energy going in, endothermic. Energy going out, exothermic. These two elements are right next to each other for the scientists who tried to create competing periodic tables. Who were the two scientists who created competing periodic tables? Mendeleev and Meyer. So I'm telling you, these are good places for me to use a clue like that because two things have to be next to each other. Questions? Okay. So now, ladies and gentlemen, down here, these two spots. These two spots are right next to each other, but what do their atomic numbers differ by? How much? How much? 24? Well, 56 to 81 is how much? Not 24. 25. Now, the reason these differ by 25 is because in this periodic table there are no what or what? No D's, no F's. No D's and no F's. So when you go from here 56 to here 81, you are differing by 25. When you go from 88 here to 113, you are differing by 25. Why? Because we've taken out the D's and we've taken out the F's. In 4 and 5, we're just taking out the what? The D's. So they differ by 11. Good. Question. Okay. We are going to cover this again tomorrow, ladies and gentlemen. Maybe, probably. Period 7, group 1. The element francium. This is the most reactive metal. That is the most reactive metal on the entire periodic table. And it is in the lower left-hand corner. Where is the most reactive non-metal? No. No, think about that. Why can't it be helium? I agree with you, Alicio. Lower left should be the most reactive metal. Upper right should be the most reactive non-metal. What's wrong with helium? It's a noble gas. Noble gases are unreactive. So where is the most reactive non-metal? Fluorine. Most reactive nonmetal is fluorine. If you get closer to francium, you will become more reactive. Now, please understand this. What I mean, potassium or rubidium, which one is more reactive? Why? Because it's further down, right? All right. Barium or cesium, which one is more reactive? Barium or cesium, which one is more reactive? Well, you're closer to francium's group with cesium, so further to the left. What I will not do is go potassium or strontium. I will not ask you to compare two things that are not either in the same period or in the same family. Same thing over here. Chlorine or bromine, which one more reactive? Chlorine is the more reactive nonmetal. Phosphorus or sulfur, which one's more reactive? Sulfur, it is closer to fluorine. So the closer you get to that spot, the more reactive you will become. Tomorrow, ladies and gentlemen, we are going to discuss trends on the periodic table and get into a little bit of Vesper. So, have a great day. We will see you tomorrow. Goodbye, goodbye, goodbye.